Oh man, look at this. Look at this. Okay. Isn't this impressively complicated?
Yeah.
That's what I love about it.
It's a cake maker, right? Milkshake maker. What are you doing?
This is cherry, strawberry. Anyway, okay. Tokamak. You know, I mean, what we do here is not that different in lots of cases. Okay, so here we are in another room, another detector. This is another endpoint where you can do an experiment. What you're actually seeing right here surrounding this endpoint is called SeGA, a segmented germanium array. And this is another place you can do an experiment. Nuclei would come down this beamline into the center of this array here. And at the center they would hit a target. And frankly, when nuclei run into each other, they can release a lot of energy. It's often in the form of gamma rays, high energy light. So yeah, hulking out is one, not really. But ultimately, the gamma rays can be picked up and therefore tell you more about the way these nuclei are interacting. These are gamma ray detectors, that's what they are. So, surrounding the point of impact, you can pick up gamma rays in many different directions. Also, some particles can continue on. We have detectors over there as well. There's neutron walls. They pick up neutrons. A lot like Mona does, only it's a different kind of scintillator, so it's a liquid instead of a hard plastic. Ultimately, you're trying to pick up some light here, some particles over there. You're still trying to put all these pieces together. What does this mean about the nucleus I'm studying? And so this is one end station to do so. Like I said, you can do sort of size, shape. They can actually set up many different kinds of detectors in this particular vault. You can do beta decay studies. How long does this thing take to decay? What's its half-life? You can do a wide variety of experiments. That's what's great about this lab. It's very versatile. And while we're setting up an experiment in this room, we could be running an experiment in another room and tearing down an experiment in another room. So the kind of transition from one experiment to the next, we try to minimize that time wherever possible, of course, because you're paying us to do experiments. This, of course, all this stuff is, in fact, cooled with liquid nitrogen and liquid helium. Here's a liquid nitrogen line. Got a little snow forming on it. I love this. We can get snowballs in the middle of summer if we want to. Basically, that just means that that particular liquid nitrogen line is not very well insulated, so water in the air is freezing onto it. But this is just a great place to see. I mean, this is how you transport nuclei. There's a pipe, you got a lot of magnets, all these white boxes, quadrupole magnets, and that arrangement of poles is how you can actually focus the beam down to a central point. So the beam size is, you know, maybe certainly less than a square centimeter. Very, very small. You want to keep it small, and that's key. And those pictures you saw earlier, they can actually see those beam spots. That's one way we can actually tell how big the beam is getting. That's important to us, of course.
Is there a limit for the detectors and how long the half-life they can detect? How should they detect the half-life?
So of course, you can detect half-life as a measure of time, and there's some experiments we do where you're actually trying to see how much time it takes. Or you can detect half-life based on the energy width of the decay. It's difficult to explain, but this much I can tell you. You might be familiar with the Heisenberg uncertainty principle. There's basically a certain amount of energy. You can either say, I can know where something is and I can know how fast it's going to a certain precision. Or you can say, I know the energy of something and the time to a certain precision. And they can tell essentially the range of the half-life by the range of energies of that particular decay. So for, say, uranium, which exists for billions of years, we didn't sit around waiting to see that. You can either get a really large amount of it and then, you know, plot the decays as they go, and so you don't need to wait until half of it's gone. Or if you have a very small amount, you can try and find out what the energy width of that decay is, and you can get a pretty good measure of the time.
There's always people that challenge the validity of how you can use
That's science.
science.
Right? That's the point.
Just answer it right there.
Exactly. Anything you do here, of course, is going to be, and this is the thing, when researchers do an experiment here, they don't pay a dime. What do they do for us back in return? They publish. They must publish what they learn. adding to the body of human knowledge. But of course, their publication is going to be reviewed, and other people are going to try to reproduce those results. This is how science works. So, don't take my word for it. Try it yourself. That's an important point. Very important. Good questions. Any others? All right. Next, I'm going to show you where we actually build our own equipment.